one of the questions that comes up when you minimize logic is how minimal is the final logic expression? So let's take a look at an example where we had a 3-input K-map, and we came along and let's call the inputs A, B, and C, and we go 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and this time I'm going to label these cells because we'll want to use those. So 0, 1, 2, 3, and we're going to go 4, 5, and then we're going to go 6, and we're going to go 7. And let's say we had 0, 1, or 0, 0 as an example, 0, 1, then we had 1, 0, 1, 1. And we came into here and we tried to put all possible circles in here. So we said, okay, I can put a circle here, I can put a circle here, and I can put a circle here. So that would be the circles that I could then use to form the sum of products. Okay. So the question becomes, well, if you look at that, was the prime implicant that covered 6 and 7 really necessary? If you had two circles that simply went like this and like this in that situation, which would be, let's call these, this is going to be 3 and 7, so this will be the 3, 7, and then this will be the 6, 4. So did we need the 6, 7? So did we need that 6, 7 prime implicant? And the answer is no, we didn't. I mean, if we didn't have that, the circuit would produce the outputs properly. We would have a circuit that, as you cycle through all the possible input codes, it would absolutely produce the right output codes. So the question becomes, how do you know when to include a prime implicant if it's redundant or something that can be removed without impacting the output? So there's a procedure that is used to find what we call the minimal sum. Now, if you use these all three, what you would do is you would create the minimized sum of products, but we want to try to find the minimal sum of products, and the minimal represents a logic expression with the least amount of operators. Okay, so how do you do this? Well, the first thing is what you're going to do is step 1 is you will insert all prime implicants. Okay, so we're going to insert all prime implicants in the K-map. And so we've done that. That's all the circles. So we had three prime implicants. Okay, so we could actually call these, we could call them the 3, 7. That's one of them. And then we could have the 6, 7. That would be this one right here. And then we could also call the 4, 6. So we have 3 of these prime implicants, and that's great. Then what we want to do is we want to identify the distinguished 1 cells. Now, a distinguished 1 cell is a cell that's covered by one and only one prime implicant. So it's covered by one prime implicant. So let's go back to the K-map, and now remember that we have all the prime implicants on the K-map right now. So that was step 1. So we have every possible one in here. So if you look at it, we go through the cells that are covered, and we have 3 is covered by the 3, 7. So it's only covered by 1, so it's actually called a distinguished 1 cell. So I'm going to go ahead and shade that in. So we have 1 distinguished 1 cell. If you look at 4, it is also covered by only 1 prime implicant, so it's covered by the 4, 6 prime implicant, so I'll cover that in. And then 6 is covered by 2 prime implicants. It's covered by the 4, 6 and the 6, 7, so it's not it's not a distinguished 1 cell. And 7 is also covered by 2 prime implicants. So what we could say here is that for this example, we'd have the distinguished 1 cells are going to be cells 3 and 4. So now we have the distinguished 1 cells. And the reason we did that because we want to then identify what we call, so this distinguished 1 cell was a new term, we want to identify another term which is called the essential prime implicants. And an essential prime implicant is something that it's a prime implicant that covers a distinguished 1 cell. Okay, so let's take a look at that and say which one is which. Well, we know that cell 3 is a distinguished one cell, so the prime implicant that covered it was the 3, 7. And then cell 4 was also a distinguished one cell, so its prime implicant that covered it was the 4, 6. And those are the essential prime implicants. So then what we can do is we can go back to our original K-map and we can remove what we call all non-essential prime implicants. So if we go back there, by identifying the essential prime implicants, these are the ones that have to stay in the circuit. Okay, there's no way to get rid of them because they cover a cell that it's the only one that covers it. So if you removed them, you wouldn't have a circuit that produced the output for row 3, and you wouldn't have a circuit that produced the output for row 4. So they have to be there. But by default, anything that is not an essential is called a non-essential. So what we can do is we can remove this other one, which is this 6, 7. We can remove this 6, 7 prime implicant, and the result will be what we call a minimal sum of products, because all that's left are prime implicants which cannot be removed, but by following this process they cover all the outputs that are associated with an output of 1. So if I draw this again really quick, what I'd have is now this. I'd have 0, 0, 0, 1, 1, 0, 1, 1, and I would have a circle here and a circle here. Now notice that all of the outputs corresponding to a 1 are covered, but I had less logic than what was up here. So we can actually form the canonical or the minimized sum of products very quickly. So let's do it for this one. F is equal to, and let's do it for this circle right here. So we're going to have right here, this covers a region where A is both a 0 and a 1, so A is gone. Covers a region where B is a 1, so I'm going to include it. So it's going to be B ANDed with C. And then this guy right here covers a region where A is a 1 and B is a 1. And then finally this circle right here covers a region where A is a 1, B is both a 0 and a 1, so it's excluded, and C is a 0, so I have that. So this is the the minimized sum of products. So B ANDed with C, ORed with A ANDed with B, ORed with A ANDed with C naught. But then when I go down here, I removed this guy right here. So this was the non-essential. So what I was left with was F is equal to B ANDed with C, ORed with A ANDed with C naught. They both give the proper output, except that one has fewer logic operations. So that's the process that we use to find what we call the minimal sum.